Good afternoon, everyone. Welcome to today's webinar on towards establishment of data-centric approach for geotechnical reliability assessment. Today, we are honored to have Dr. Andy Leung, who is a current associate head and associate professor at the Department of Civil Engineering and Environmental Engineering at the Hong Kong Polytechnic University. His research interests include soil structure interaction, reliability of geotechnical and structural system, probabilistic analysis approach, and novel geotechnical instrument technologies. So without further ado, may I invite Dr. Andy Leung to present the topic today. Thank you, Dr. Leung.
Thank you very much for the kind introduction. Good evening, everyone. Thank you for coming. And it's my pleasure to be here to share with all of you the current work that we're doing at PolyU. And I hope this is going to be a timely topic when everybody starts to appreciate the value or the importance of data. And then today we'll be discussing this in the context of geotechnical engineering. Right. So just to start with a bit of background. Okay, so right. So this chart here on the left-hand side that you will see is coming, well, it came from a survey for some project managers in the United Kingdom some 20 years ago. And in that survey, the respondents were asked a question: when they have a geotechnical project, what is the usual cause of the problem if they encounter any? And then quite interestingly, most of the problems that engineers encounter in geotechnical projects, they did not come from the detailed design, they did not come from the groundwater or calculation methods. Most of the problems, some 40% of the problems, actually came from the fact that they did not know the soil boundaries very well, and they did not know the soil properties very well. Or in other words, even if you have a very good software or analytical method, you don't really know what parameters you should put into your analysis. And this is quite well known to be a very important source of uncertainty or trouble when it comes to geotechnical engineering projects. So on the right-hand side, I'm trying to show another example. Let's say now we are talking about slope engineering. Quite often we try to calculate a single factor of safety to indicate how safe your slope is going to be. It might be 1.3, 1.4, and so on. If we use this single value of FOS, we call this a deterministic approach. But because soil properties or rock properties are usually quite uncertain, actually the uncertainty in the properties of material will eventually give you an uncertainty in your evaluation of FOS. So if we take two slopes as examples, for example, if you have a slope 1, the blue line, it might have a lower value of the best estimate of FOS. In this case, this best estimate may be roughly 1.5. And then because of uncertainties in soil properties, the FOS may also distribute a certain uncertainty, which is indicated by this blue PDF line. And then on the other hand, you might have a different slope, slope number 2, which will have a higher value of the best estimate factor of safety. In this case, this might be about 2.0 for the best estimate of FOS. But this slope 2 may be associated with a larger uncertainty in soil properties, which means you have a higher uncertainty in your FOS estimate. So your PDF or probability density for FOS will be shown by this orange line, which is much, much wider with more dispersion. So if I ask a question, slope 1 and slope 2, which one is actually safer? If you use a deterministic approach, you only consider the mean FOS, you might say slope 2 should be safer because the best estimate factor of safety is larger. But if you take into consideration the uncertainty in your estimate, you will see that Between these two curves or these two PDFs, the orange one has a larger area that falls into the region where FOS is smaller than 1. Or in other words, we could say that slope 2 actually have a bigger chance or bigger probability to fail. So if we take into account uncertainty of properties, slope 2 is actually less safe. So here, I hope that gives you a simple example of how uncertainty in the material properties actually affects ultimately the safety of the system. And it is quite well known that geotechnical properties, soil properties, are associated with very significant variability. So this table here was taken from a publication roughly 25 years ago. So on the left-hand side, we are talking about properties of soil, such as undrained shear strength or friction angle or tangent or friction angle for different soil types. And then even within the same site, if you talk about the SU, the property value can range from 6 to 400 kPa, which means a really, really wide dispersion of the data. Friction angle, for example, even in the same site, it could vary from 17 to higher than 40. So soil properties are associated with very significant variability. It's basically a known fact. Here, we introduce one more parameter called COV, which I'm going to define in here. Oh, sorry, on the next page. So we're going to talk about COV later on. And in the current practice, we know that if we do a lot of geotechnical investigation, we may get data points with a very wide dispersion, which might be the white circles in here. In the current practice, quite often we try our best to fit a certain trend line, or maybe we try our best to get a certain lower bound or a certain design profile close to the lower bound. But when we're doing that, we basically, we're not rigorously considering all this sort of variability and uncertainty that is being displayed in the soil data. So the question is, can we do something better? Can we try to use a more quantitative approach to consider all this variability and how that might affect our uncertainty in engineering performance? So here we go back to some basics in statistics. So if you have a data set, it's very simple for you to calculate the mean value of those data points and also calculate standard deviation of those data points. And 2 pages ago, we talked about this parameter called COV. COV in full is called coefficient of variation. It's basically just the standard deviation divided by the mean value. Or in other words, it's trying to tell us the amount of dispersion in the data sets when compared with the mean value of the data set. So if we go back 2 pages ago, for properties such as undrained shear strength, the COV, the dispersion, can be roughly 20 to 30% compared with the mean value of the shear strength. For friction angle, you can also have something like 10% to 20% of COV, which again is just standard deviation divided by the mean value. So there's a lot of dispersion in geotechnical materials. If you are familiar with structural materials, concrete and steel, for example, usually the properties of concrete or steel might be associated with COV of roughly 10% or less. Whereas for soil properties, this COV could be 20, 30, 40% quite easily, much, much more variable in geotechnical materials. So the objective, well, one of the goals here is that can we try to use high quality test data of soils, for example, in Hong Kong, so that we can characterize the variability of materials in Hong Kong so that we can have a better estimate in terms of the uncertainty in our system performance and the probability of failure or the associated risks may be better characterized if we have a good understanding in the uncertainty of our own material. So that comes to the next part of this presentation, which is to look into variability in data coming from our geotechnical investigation. So here are just some photos, just to remind us again how variable geomaterials, soils, and rocks can be. Obviously, these materials, you can easily tell that they're quite non-uniform or heterogeneous, if you like. And in fact, over the years, the Geotechnical Engineering Office, or GEO of CEDD, has compiled a good amount of data from different parts of Hong Kong. GEO, for example, they manage a lot of slope projects across Hong Kong, and there are a good number of GI fieldwork reports and also laboratory test reports. And they have recently compiled all this into a digital platform, which they call the DGIU, Digital Geotechnical Information Unit, which gives us a web-based platform for engineers to easily extract data from different parts of our city. And then most of you already know that in Hong Kong, the level of geotechnical control is very good. So when it comes to GI, drilling, coring samples, or obtaining block samples of the soil, we have a very good standard, GeoGuide 2 or GeoSpec 3, which tell engineers the best practice in terms of retrieving soil samples and also conducting laboratory tests on those samples. So from all these data sets across Hong Kong, we have got high quality samples and also high quality laboratory test results to help us characterize the material properties, or more importantly, the variability of material properties across Hong Kong. So let's take a quick look on the distribution. So this pie chart here basically tells us the number of data sets that we already compiled, actually what GEO already compiled for different types of soils in Hong Kong. So we have a good database for fill material, a colluvium database with more than 800 data points, CDG 750, CDV 650, and so on. And these numbers here actually indicate the numbers of multi-stage consolidated undrained triaxial compression test data. So when I say 750, that basically means we have got for CDG 750 combinations of cohesion and friction angle, which are based on the triaxial test results across different parts of Hong Kong. So so here, well, today we probably will focus more on this CDG database because we've done some work using this quite comprehensive set of information. Okay, so of course, if you have got 750 samples, C5, and so on, it becomes very straightforward for us to plot those data, calculate the mean value, standard deviation of cohesion and friction angle, and then figure out the coefficients of variations like we defined before. So just very quickly, for different soil types, the mean values of cohesion may vary from somewhere around 6 kPa to about 12 kPa. That's the mean value of cohesion. And then the standard deviation is roughly 60 to 80% of the mean. Again, that's the definition of COV. And then similarly for friction angle, the mean value from these large data sets, the mean value of friction angle are also listed on this table. And sometimes we might notice that the two parameters, cohesion and friction angle, there might be some sort of a weak correlation between these two parameters. So all these tables And then data set we have published some years ago, like 2 years ago, in collaboration with colleagues in GEO. And of course, you can easily calculate mean and standard deviation from this data set. You can also very easily plot this up into a histogram. So this one is a histogram of the cohesion values together with the fitted probability density function here. And then we can do similar thing for friction angle, which looks like a normal distribution. And then they are the shear strength parameters for the colluvial soils in Hong Kong. And the right-hand side, of course, you've got CDG. Again, you can plot up the histogram and probability density function for the cohesion values and also friction angle based on these extensive sets of Traxel test data. So all these are actually quite straightforward. With these good data sets, it's very easy to do. But now we want to go one step forward beyond just cohesion and friction angle. If you think about the origin of these data sets, they were from slope projects where the main concern is to calculate whether the slope fails or not. It's a slope stability limit equilibrium calculation. So the most important things are, of course, the shear strength parameters, cohesion, and friction angle. But there are also a lot of geotechnical or civil engineering projects where the concern is not just failure or not, it's not just collapse or safe, it's also, well, the concern could also be the displacements of the ground. In that case, if you want the soil or rock displacement, you can't just rely on shear strength parameters. Everybody will know that at least you need some sort of stiffness, Young's modulus values to help us calculate displacement. So that's why we took those data sets, 700 and something sets of Traxel test data. We tried to go into more in-depth analysis to try to understand the entire stress path and also the stress-strain relationship, the stress-strain response, such that we can also determine the stiffness parameters, or more importantly, the probability distribution of the stiffness parameters. So we go into lots of the details of all those sets of multi-stage consolidated undrained Traxel tests. And then we also try to look into how well we can simulate those test data using different constitutive models. So first of all, we start with a simple model, which is the familiar Moore Coulomb model. So well, most of you will still remember from school that Moore Coulomb model, you have the shear strength parameters, and then you also have some stiffness parameters, Young's modulus and Poisson's ratio. And we also introduced the dilation angle to simulate the post-yield behavior. But then in simple words, the Moore Coulomb model in terms of the stress strain curve on the right-hand side is going to give you a bilinear relationship. So when the strings are small, you have a modulus here. When it comes to the yield behavior, you get a different slope, which is characterized by the dilation angle. So that's the simple Moore Coulomb theory in terms of the stress strain curve. So we try to see whether this particular model can match our experimental results well enough. And apart from this simple Moore Coulomb bilinear stress strain model, we also introduced or adopted another more sophisticated model, which is based on the critical state soil mechanics. So this model in particular is called a North End model, so which was proposed by Dr. Jeffries in the UK in 1993. So I'm not going to go into all these details of yield surfaces and the complicated details of the constitutive model. But then in simple words, this model allows us to understand or to simulate the more nonlinear behavior of the soil stress strain response. So hopefully we're going to get something like this. We're going to use this model to help us simulate a very highly nonlinear soil behavior. So that's what we want to achieve using this slightly more complicated constitutive model. So for those of you who might not be very familiar with critical state models, basically this North-End model includes these model parameters. So if we go back to Moore Coulomb, we know that there are basically 4 or 5 parameters: the shear strength parameters and the stiffness parameters. When it comes to critical state model, North-End, we have in total 7 parameters. Some of them are related to the shear strength. Some of them are related to the elastic modulus. Some of them are related to the yield behavior, the yield function, yield surface, and so on. So I'm not going to go into too much details in terms of these theories. But then the main message here is that we have got a lot of triaxial test data. We want to be able to simulate or calibrate the parameters so that we can predict the entire stress path and also the entire stress strain response of the realistic soil behavior. So you might still remember that across Hong Kong, we have got some 750 sets of triaxial test data. But then now we're really looking into a lot of the details. So we have to start from somewhere. So instead of using all the 750 sets of data, we now focus on a certain zone or area or region within Hong Kong, which is here in the Kowloon area. So we only looked at the data sets around this area, which gave us roughly 100 sets of triaxial test data. And we really look into all the details of the stress path and stress strain curve and see how the 2 different models predict the soil behavior. So this is how it looks like. So this is one example of a specimen of loose soil material. So we use both the Moore Coulomb model and the more complicated North-End critical state based model. And we try to see how well we can match or calibrate, well, match the stress strain response and also the entire stress path for the multi-stage triaxial test. So in this case, the Moore Coulomb did all right. So the discrepancy between the simulation and the actual data is roughly 8% or so. It's not too bad. And then the North-End model actually gave us a better match, a slightly better match. Again, the blue is the test data. The red is our simulation. This is the stress strain, and this is the stress path response. And the orange here actually indicates the yield functions at different stages. But then for the purpose of today, we don't have to worry too much about these orange yield surfaces. In simple words, the North-End model in this case gives us a slightly better match, a smaller discrepancy of about 4% in the case of a loose soil. And this is how this loose soil actually look like. But when we look at a different soil specimen, in this case, a medium dense soil, this is where the North-End model really shines. Or in other words, this is where the simple Moore Coulomb model couldn't really capture the realistic response. So the blue line again is the actual test response, and the red line is the best that the Moore Coulomb model could offer. So you can see that there's a quite significant discrepancy between the actual and the Moore Coulomb model prediction, both on the stress strain response and on the stress path prediction. discrepancy quantitatively is about 20%. And then the critical state, the north-south model, gives us a much better match with the reality when we consider the special features of our CDG material, which in this case is a silty gravelly sand material. So here the discrepancy is still less than 4%. So we did a similar exercise for 100 sets of traxel test data. And then if this is the distribution or the probability distribution of the north-south model parameters. And we also managed to fit the PDF, the blue line here, to show the amounts of variability when it comes to the material parameters for the 100 sets of CDG tests. And then, of course, if you can fit the PDF, you can actually get all these mean, standard deviation, and different types of probability distribution function. But I guess more importantly, if we use this more sophisticated north-south model, the discrepancy between the model simulation and the actual test results is roughly 7% on average. So in other words, on average, this model will be within 7% of the actual soil behavior as we observe in the laboratory. So this is a way to show that our calibration is working quite well. And this is also a way to see that, or to say that the distribution of the parameters that we show here is realistic. We can take that into consideration if we want to understand variability of the soil parameters, particularly for the CDG in Hong Kong. So that's one of the main purposes of this exercise. And then with that, I'd like to go to the second part of today's presentation, which is how this material variability or material uncertainty, how that will be reflected into the response of the system. So basically, if you have a certain uncertainty in your material property, if you put that uncertainty into your calculation model, which might be your finite elements, finite difference, or other types of calculation model, you will then get to understand or obtain a certain uncertainty in your system response. This may be an uncertainty in your FOS of slope stability, or it might be an uncertainty in the displacements of the ground when you have an excavation or foundation project, and so on and so forth. So now we try to look at how this material uncertainty will eventually propagate into your system performance uncertainty. To do that, we want to again take a closer look at this photo. So here we can see that the materials are not homogeneous, they are not uniform. But then if you look a bit more closely, you'll probably see that this degree of heterogeneity actually also varies along different directions. In this case, this figure B, you have got a layered system of materials. When we say layered system, what we really mean is that if you look across a vertical direction, the material properties change very, very quickly. But then within the same layer, in the horizontal direction in this case, the material properties are more or less uniform. So this basically means that the variability, the degree of variability can also change when you're looking at different directions. And then of course, you can have horizontal layering or you can also have inclined layering in rock layers, for example. So the main message here is that when we look into variability of materials, this variability can give us different patterns along different dimensions of your subsurface profile. And all these can actually be modeled mathematically as well. But then for today, I don't want to go into too much of the mathematical details. On this page, I really just want to point you into a specific parameter which we call theta. So earlier in the first part of the presentation, we talked about mean value, standard deviation, coefficient of variation. But here, this theta value tells us how smoothly or how quickly material properties vary across space. So if you look into this diagram on the right-hand side, so this one and that one, they show us two different cases of theta value. In simple words, if a theta value is large, the variation of material property is smooth. Okay, so which is the right-hand side here. If the theta value is small, that means that the material properties vary suddenly or very quickly in the spatial sense, which is a lot of fluctuations in terms of material properties. So that's basically the physical meaning of this parameter theta. If you want, the name is autocovariance distance. And then from the previous page, we saw that the pattern can be different along different directions, which also means that the theta value can be different along different directions. And then if we put that into a mathematical sense, we can try to model the variability or correlation of soil properties in three directions with different theta values. And figuratively, we can have larger theta values along the horizontal direction, theta 1 and theta 2, and then relatively smaller theta value in the vertical direction, which I put as theta 3 in this diagram. And then if you can have different values along the different principal directions, then mathematically you can figure out what happens in theta along all other orientations, which is basically what we're trying to represent in this ellipsoid in the three-dimensional space. But if we try to put that in a more simple terms, what that means is if you have theta values or the combination of theta values like this, it will be reflected into variation of soil properties like in this contour. So this red, green, and blue contour basically is indicating the variations of soil property, which might be the stiffness or the friction angle, etc., etc. So we can model, in one case, we can model the soil properties varying along horizontal layers. In another case, we can also mathematically model the soil properties varying in an inclined orientation. So that's how you see the different patterns of the variation in soil properties. So this all could be done if you can figure out the theta values based on your site data. And then more importantly, we can put all these into geotechnical scenarios, making use of the technique called random field modeling. So on the left-hand side, here we try to model layered soil with different properties with depth. And then we try to understand in this situation, how does the shallow footing respond in terms of the footing displacement or bearing capacity. So we can make use of the idea of Monte Carlo simulation to generate many different possible soil profiles that satisfy the specific features of theta that we define. So this is trying to put together to try to understand the footing response on top of spatially variable soils. And then on the bottom, we're trying to understand how these variability of shear strength parameters is going to affect slope stability in different situations. And then there could be many other different things that we can do with these mathematical skills. So we can try to see if you have a soil profile, which is varying in three-dimensional three-dimensional space, how that is going to affect your deep excavation project in terms of your struct force or retaining wall deformation and so on. We can also try to understand how the variability of soil properties will affect slope failure. Because generally, if you just take a two-dimensional slope analysis, you're basically saying that along the longitudinal direction, you have a plane strength problem where if the slope fails, the entire slope will fail altogether in the longitudinal direction. But if we consider the variability of soil properties carefully, we can observe that generally there might be weak spots along your slope that fails instead of the entire embankment coming down altogether. So these are all different things that we can, or different models that we can construct to try to understand how soil variability affect the system response. But here I want to spend a little bit more time to talk about two specific case. The first one is a deep foundation case in Germany. So this tower, I can't speak German. So this tower here was constructed in 1993, 200 meters tall, supported by a power raft with 40 friction piles. So quite unlike Hong Kong, in Frankfurt, the bedrock level is very deep down. So many of the piles were actually frictional piles that are embedded in Frankfurt clay. So there have been quite extensive reports of the foundation response analysis, and it was also observed that there is a tilting of the tower or tilting of the foundation with an amount of about 1/1600. So basically, if you carry out deterministic analysis, considering uniform soil properties or uniform layering of the soils underneath the tower, you really can't obtain a tilting in your foundation if you talk about uniform horizontal layers of soil underneath the foundation. So we try to see whether we can develop a probabilistic approach to understand this problem. So again, I'm not going into details of the analytical approach of how to calculate the foundation response and so on. But essentially, the main point here is that we incorporate the subsurface soil profile and we try to model the variation of the soil stiffness and soil strength underneath the foundation. And at the same time, we also take into account the foundation problem, the power raft with 40 piles supporting the superstructure 200 meters tall. So we try to see that whether this variability or variation in soil properties will give us the tilting response of the tower. And the thing is, because we can model different soil properties varying underneath the foundation, we can get the probability density functions of the foundation settlements at the center, the maximum and minimum power forces that were measured by the engineers there. And also, we were able to estimate the amount of tilting that might happen in the foundation due to the variability of soil properties underneath. And then here, of course, the gray ones are the PDF, the probability density. And the black line here is the actual measured value in Germany. And then the one I would like to highlight is actually this figure B on the right-hand side. We were able to estimate the foundation tilting, which generally matched with the measured tilting response reasonably well. So we're quite happy to see that we're able to say that considering the variability of soil properties, we might be able to explain why the foundation tilted after the tower was constructed. The second case that I want to spend a little bit more time on is a landslide case back here in Hong Kong. So many of you will be familiar or will have heard about this Ching Chun Road landslide happened in 1997 after a heavy rainstorm during a typhoon event. And then at that site, actually there were some GI and drilling and laboratory testing, and there were 25 sets of site-specific Traxel test data at this Ching Chun Road slope site. So in this situation, well, in this case here, you might ask yourself, now you have got 25 sets of Traxel test data. What would you do to try to understand the slope stability? Of course, the conventional way will be taking the 25 sets of test data, try to obtain the so-called reasonably moderately conservative combination of cohesion and friction angle, and put that into your slope W or slope stability analysis software and calculate a single factor of safety. But we want to try to do that in terms of a probabilistic manner, try to understand the mean estimates of factor of safety, or calculate what is the probability of the slope failing, considering these test results. And there are actually three possible options we can consider. One is to say, like I said earlier, we know in Hong Kong there are already 750 sets of data points of C5 based on previous projects across the entire city of Hong Kong. That's method one. Option two is to say, now we have got 25 sets of Traxel test data at your Ching Chun Road site. We try to fit a histogram or probability density based on the 25 sets of data, and then again estimate the probabilistic or the PDF of factor of safety. And method three is to say, can we not combine our previous knowledge or regional data and then supplement with the site-specific data to get the best of both worlds? So that's what we call a hybridization approach. So we're trying to see how these three different approaches will give us maybe different insights. So when it comes to the idea of hybridization, it actually didn't come from us. It was proposed some years ago by professors in Singapore and in Taiwan, and the idea is that if you have some generic PDF, which is the previous knowledge indicated by the black line in here. So this might be referring to the previous 700 data sets in Hong Kong. If you don't have any site-specific data, then you will simply make use of the previous knowledge, which makes sense. On the other hand, the black line here still shows your previous knowledge of 700 datasets. But if you have a case where you have a lot of site data, you will combine your site data with the regional previous knowledge to combine it into a so-called hybrid PDF, which will be heavily influenced by your site-specific knowledge if you have plenty of site-specific knowledge. So that's the idea of hybridization. And then we make use of these similar concepts, take into account the range of 750 datasets across the entire Hong Kong, try to do some sort of a smart analysis. And then we propose an approach called hierarchical Bayesian model, basically to combine the city-wide data across Hong Kong with the site-specific data around Ching Cheng Road with the 25 sets of data. And we try to see how different they would look like. So first of all, if we only use the previous knowledge, we get the black line in terms of the probability density of factor of safety. So the region or the area left-hand side of FOS equal to 1 will be the unsafe region. So if you integrate this area, you get the probability of failure. So the idea is that if we hybridize the previous knowledge with the site-specific knowledge, we get a quite different probability density of FOS indicated by the blue line. And in this case, you're going to get a much higher area in the unsafe region or a much higher probability of failure. And then at the bottom, I probably won't spend too much time on this one. We also compare with the case if we only take into account the 25 sites data. So basically what this chart here means is that if you only take 25 sites data, you might get a you might not get a robust estimate in terms of the factor of safety because 25 site data may not be fully representative of the entire site. But then if we can consider both the regional and the site data and combine and hybridize, we will be able to get a more robust estimate in terms of factor of safety and also the probability of failure. I'm quite aware of the time, so I might not be able to go into the full details of all these analysis, but the idea is that we're trying to propose a way that will allow us to consider both the regional previous knowledge together with the site-specific data, combine them to give us a hybridization of the information. So coming to the very last part of the presentation, previously we've talked about how we can analyze the existing database of Traxel tests. We also briefly touched upon this Bayesian approach to help us combine previous knowledge with new data. And the final part here, we're going to talk about new ways to help us measure or generate data based on the measurements of infrastructure response. So I'm going to be quite quick in the final parts because some years ago I gave a similar presentation in the Geotechnical division of Hong Kong IE. I don't want to repeat too much of that here. But then for the benefits of those who may not be Geotechnical division members, here in PolyU, currently we are doing a lot of work in terms of uh, infrastructure monitoring using fiber optics technology. So in simple words, in the conventional way, if we want to measure the strain inside your infrastructure, your pile, retaining wall, columns, and so on, quite likely you'll use a strain gauge. And then strain gauge will give us a points-wise measurements. In other words, where you place the strain gauge, you only get data at that location of the strain gauge. So the other technology is called the distributed fiber optic sensing technology. And the good thing about this technology is that if you have a continuous fiber optic cable, which might be 50 meters long, you will be able to get continuous profiles of the string along the entire cable, 50 meters, for example, with a spatial resolution up to something like 1 millimeter. So it could be 50 meters of measurements, and you get data every single millimeter. So that's 50,000 data points along the fiber optic cable. So that gives us a very large volume of data points to do data analysis to help us understand the behavior of your structure or geo infrastructure along the entire length. So we have recently applied this technology in a project called the T2 trunk wall project. Basically, this excavation is for the launching shaft of a tunnel boring machine. And because this is in circular shape, we want to be able to measure the hoop strength developing along the diaphragm wall. In other words, we're trying to measure the compression along the lateral direction of the retaining wall panel. So it's very difficult to do that using strain gauges. So that's why we use this fiber optic technology. If we take this as an example, this is the diaphragm wall panel. Now we're trying to measure the horizontal compressive strength. So we can arrange our fiber optic cable in the horizontal pattern. These horizontal sections here gives us the horizontal strength in compression for the along the entire diaphragm wall. So the cables that we use in this project, they look somewhat like this. So actually, in reality, these cables, they're actually like 5 millimeters in diameter, just like your any electrical cable. But then inside, we've got the fiber optic core surrounded by this steel armor. So these are quite strong and can survive the environments of a construction site. So most of these cables actually survive and give us pretty good readings. So the next page just shows some of the preparatory work that we did in our laboratory, some calibration work before we bring the instruments to the site. And this photo here shows what the process when we're obtaining the data of the strings inside the fiber optic cables. And then this page shows how the data looks like. So this one is basically coming from this diaphragm wall panel where we just put some vertical cables on the front side and the back side of the retaining wall. So what the fiber optic cables measure are actually the axial strengths. So if you consider that your wall panel is bending, it has a certain bending moment, it's going to give you different axial strength measurements for the front side and the back side. And the different colors here basically correspond to different stages of the excavation. So using these differences between the strengths in the front side and the back side, we'll be able to calculate the curvature and therefore the bending moments. So stage 1, the curvature is represented by the black line here. And then stage 2, if a top-down construction, so we have a slab at the top and some excavation, and this curvature in red is captured by the fiber optic readings in red. And stage 3, more excavation, the green profile of the incremental curvature is also captured by the green profile by the fiber optic measurements. Similarly, we go down deeper, stage 4, stage 5, 6, 7, the curvature in different colors. They are also captured by the readings of the fiber optic cables. But then more importantly, we're trying to measure the horizontal compressive strength. So that's why we have the horizontal sections of the cables. So now we're talking about the hoop strength, which should be in compression. So in these 6 sections of the horizontal cables, we're able to see 6 profiles of the compressive strength. And then again, the different colors basically correspond to different stages of the excavation. And then we see that we have cables arranged on the front side and also cables arranged on the back side of the retaining wall. And they actually capture different magnitudes of the compressive strength. The front side here, a bigger compression, and then the back side here, a smaller compression at different construction stages. So if we take a moment to think about why this happens, it's basically because just now we said that if you have bending of the wall in the vertical direction, you have different strengths in the front side and the back side. And if you have a bending in the horizontal direction of the wall, you will also have difference in the compressive strengths comparing front side and the back side. So by doing these measurements, we're actually able to capture the bending of the wall along the circumferential direction when you have a circular cofferdam utilizing the hoop action to support the excavation. So this is quite interesting behavior that we capture. So we published that in a recent journal article. And the main message here is that by using these new instrumentation methods, we were able to have a new way to generate large amounts of data to understand our infrastructure behavior, which we wouldn't have been able to do before. And then after that project, we are also trying to apply this fiber optics technology in many different types of infrastructure or geotechnical engineering project. We are considering to do that in some MTR projects. Well, we are still in discussion for that. But then we are also currently doing this in certain bore power projects, also some tunnel and cavern developments, and also some laboratory developments to try to review different aspects of soil structure interaction in different scenarios. So coming to the summary, so this is the last page of the presentation. So here in this presentation, we talked about new ways to interpret data sets of conventional traxel tests or geotechnical elements testing. We also discussed new ways to analyze data with some Bayesian machine learning for decision making to understand how variability of soils will change our perception of the risk of the project. And we also discuss some new ways to help us generate new types of data when it comes to understanding infrastructure behavior. And all these, they're actually somewhat related to each other. So we want good data sets to give us good analytics results. And then we also need these data analytics tools to combine with different source or new sources of information to give us a better risk-informed decision making. And then ultimately, we also want these new data sets or new types of data source to give us a better understanding on various aspects of soil structure interaction so that our knowledge or experience in our soil variability, soil properties can be properly reflected into how we understand infrastructure behavior. So this is actually the last page of the presentation. So I just want to thank again the collaborators, particularly from the Geotechnical Engineering Office of CEDD. And this project was sponsored by the Research Grants Council. And then lots of my research students, RA, and colleagues in PolyU also helped in all these developments. Just want to thank all of them for helping to prepare this work. So that's it from me. So if you have any questions, please feel free to raise that in the Q&A, and I try to respond to the best of my capabilities. Thank you.
Yeah, so thank you, Dr. Leung, for your presentation. So we have got, so for the participants, so if you have any questions, please leave your questions in the Q&A section. And now we have one question. So I will read out. So dear Dr. Leung, do you have any simple way to estimate the slope stability based on the soil properties? For example, once we know the shear stress of soil or properties, we can know the maximum cut slope angle would be, as we can only run the program or cut the slope in different slides to calculate the factor of safety.
Oh, okay. This is an interesting question. So do we have a simple way to calculate slope stability? So I think in general, the most common way in practice these days is to use the method of slices. So for example, there are software like SlopeW to help us do that. So this is the way that is generally accepted in local practice. But then you mentioned that if we know the shear stress in the soils, in theory, if you already know the shear stress in the soil, you can compare this maximum shear stress with the shear strength of the soil. And then that will give you a quick estimate in terms of the factor of safety. So, but the tricky part is that if you change the cut slope angle, you are then going to change also the shear stress of the soil. So shear stress actually depends on the angle of the cut slope. So, right, so yeah, there might not be a very simple way, or there may not be a simpler way compared with method of slice that is generally universally accepted in the practice. Yeah, I guess that's my thoughts about this one.
Okay, thank you, Dr. Leung. So do we have any more questions on the floor? So I guess not. And so thank you, Dr. Leung. I guess we will end the seminar here.
Thank you. So, of course, if you have further questions, feel free to send a message or give me a call. Happy to discuss different aspects of the presentation or different aspects of data or measurements or instrumentation in different types of civil engineering projects.
Sure thing. So on behalf of Hong Kong IE Civil Division, thank you, Dr. Leung, again, and hope to see you again. And if you have any more questions, feel free to drop us an email. Okay,
Okay,
that'll be all
thank
for
you.
today. Thank you. Cheers. Bye.
Thank you.